this is question number 1. A particle in a cubical box with infinite potential barrier outside, this usual cubical box, is elongated along z-axis to a small extent. If the energy of the particle before elongation is this, then the energy state having least energy after elongation is. Okay. Now listen, for this energy level, this is before elongation. Okay, before elongation, this is the energy of the particle. For this energy level, what are the states available? First, we should find out that. Okay, so we'll discuss the answer here. First, for this 11h square 8ml square, what is the degeneracy possible? You know very well, this is nothing but nx square plus ny square plus nz square into h square by 8ml square. This is the energy formula for a perfect cubical box, and the energy is given here 11 times h square by 8ml square. So these two cancel. So nx square plus ny square plus nz square should be equal to 11. Okay, which value of nx, ny, ny, nz will give the answer as 11? We should find out. Okay. Yes, how to do this? Yes, listen. So, what are the values of nx, ny, nz? Will give me nx square plus ny square plus nz square as 11. Nz square as 11. So, this we should find out. Yes, this is very quite easy. So, you take this combination 3, 1, 1, 3 square plus 1 square plus 1 square. Yes, this will give me 11. Okay, so 3, 1, 1 is one state. What are the other possibility? 1, 3, 1 is another state having the same 11. 1, 1, 3 is another state having the same ns square plus ny square plus nz square as 11. Okay, therefore, apart from these three, there is no other states possible which give the total value as 11. Okay, therefore, degeneracy is equal to 3. Right? So, the energy level 11 h square by 8 ml square has 3 states. 1, 2, 3. What are the 3 states? State 1 has quantum numbers 3, 1, 1. State 2 has quantum numbers 1, 3, 1. State 3, 1, 1, 3. Okay. This is the energy states available at the energy level 11h square by 8 ml square. This is before elongation. Now, just go through the question clearly. If the box is elongated along z-axis, it is elongated z-axis in small extent. You know very well, if you elongate, whenever we elongate the particle, energy of the system will decrease. Now, the elongation is carried out along z-axis. Okay, so the box is elongation along z-axis. That means, among the 3 states, you see nz quantum number. Here nz quantum number is 1, here 1, here nz value is 3. Nz quantum number having maximum value, that state will go to the lower energy level among the 3. Okay, among the 3, so this is the energy state or energy level before elongation. Because of elongation, all the 3 states will lower in energy. Out of the 3, this state, 1, 1, 3 state where nz value is maximum, that goes to very low energy among the 3. So, this is 1, 1, 3 state. The other 2 states for which nz value is same, therefore their energy will decrease, but they remain degenerate. 3, 1, 1 and 1, 3, 1. These 2 states, they remain degenerate. The one in which nz quantum number has maximum value will go to lower energy. So, among the 3, the one which has lowest possible energy is 1, 1, 3 among the 3. Okay? Yeah. So, the question asked here is, then the energy state having least energy after elongation is. So, the least energy is option E, 1, 1, 3 state. Okay?
Sir,
This is the question number 2. The potential energy of a one-dimensional simple harmonic oscillator is. Right, listen, this is actually a simple problem. You know very well, for one-dimensional simple harmonic oscillator, it obeys Hooke's law, right? One-dimensional simple harmonic oscillator obeys Hooke's law. Therefore, we should use the formula for Hooke's law, and we should derive from that. Listen, you know very well, according to Hooke's law, the restoring force is directly proportional to minus the displacement. Okay, so whenever a molecule undergoes elongation means the two atoms moving away, right? Whenever a molecule undergoes elongation, some force will act in the opposite side. See, elongation occurs in this direction, but the force will act in the opposite direction, which try to keep the molecule in the equilibrium geometry. We call that force as restoring force. Restoring force is directly proportional to minus of displacement. See, displacement occurs in this direction, whereas the force acts in the opposite direction. That's why we put minus sign. So F is restoring force, X is displacement, and the minus sign indicate force and displacements are in opposite direction. If I equate this, we should introduce a constant. Yes, the constant is nothing but K. Where, see, F is restoring force, X is displacement, and K is called force constant of the bond or force constant of the spring, right? If it is a pendulum-like oscillator. Okay. Now, we also know that force is nothing but minus change in potential energy due to displacement or with respect to displacement. Okay, force is also equal to minus change in potential energy with respect to displacement. Since these two forces are one and the same, if I equate this, we get dV by dx equal to K into x. Now I'll bring this dx to the right hand side. So what we get is dV equal to K into x into dx. Now for a small displacement, we'll get small change in potential energy. For finite displacement, you have to integrate. So if I integrate this, I'll get integral dV equal to K is a constant, keep it out, integral x into dx. Integral dV is V, K, keep it as such, x into dx, if you integrate, you will get x square by 2 plus we should include as integration constant C. Okay. To find C, what to do? Put x equal to 0. X is equal to 0 means no displacement, meaning the molecule is in the equilibrium geometry. When the molecule is in equilibrium geometry, then the potential energy of the molecule at the equilibrium geometry is assumed to be 0, which is actually lower in energy, lowest energy. We assume normally it is 0. So at x equal to 0, if I put x equal to 0 here, this quantity becomes 0. At x equal to 0, right, V also becomes 0. Right, since V 0 and this quantity also 0, therefore it implies that C is equal to 0 in this case. If C is 0, substitute the C here, therefore potential energy is equal to Ka x square by 2. Yes, this is the potential energy of one-dimensional simple harmonic oscillator. So this oscillator is oscillating only along x-axis, so it is called one-dimensional. Okay, it undergoes elongation, compression, right? It is occurring only in the x-axis, so it is called one-dimensional, right? And potential energy is given as V is equal to Kx square by 2. This is the potential energy of a one-dimensional simple harmonic oscillator. So the correct option among the three is option C. Okay, take note. This is question number 3. The energy gap between n is equal to 10th vibrational state to the ground vibrational state of a diatomic molecule is. Assume the molecule as one-dimensional simple harmonic oscillator. They are asking energy gap between n equal to 10th vibration state to the ground vibration state. Okay? Yes. How to find out? Question. Listen. They are asking energy gap. Gap between n is equal to 10th state to n is equal to 0 state. N is equal to 0 is the ground state. Okay. Now, listen. What is the energy formula? You know very well. N plus half into h nu for one-dimensional simple harmonic oscillator. This is for higher level minus n plus half into h nu. This is for lower level. Let me write this as say n prime higher level and this is n double prime lower level. Where n prime, n double prime are vibrational quantum numbers. Okay. Now, which is the higher level here? N is equal to 10. So put n equal to 10 here. 10 plus 1 by 2. So 21 by 2, correct? 21 by 2 h nu minus, if you put n double prime for ground state, n double prime is 0. If you put 0 here, 0 plus 1 by 2 is 1 by 2 h nu. Right? Now, if you take LCM, so by 2, so 21 minus 1 is 20, 20 by 2 is 10 h nu. 10 h nu is the answer. Okay? So the correct option for this question is option A. Is this clear to all? This is the next question. The ground state energy of a particle in 1D box. This is normal 1D box. Where potential energy inside the box is 0, outside the box is infinite. On the wall, outside the wall it is infinite. Question is the ground state energy. Remember, box length, see this? Box length, what is the box length? The final value is n by L by 2 minus initial value is minus L by 2. So I will get the box length as L. If box length is L, then energy formula does not change. So what is the energy formula? En equal to n plus half, n square h square by 8 ml square for particle in 1D box. Energy formula remains same because box length is L. Okay. But remember, only energy formula remains same, not wave function. Wave function will differ. Okay. I have already discussed that, as you know very well, right? What is the wave function? Now, for the ground state, put n is equal to 1. If you put n equal to 1, right, we will get the ground state energy. So what is the ground state energy? H square by 8 ml square. So ground state energy for this particle in the box is also h square by 8 ml square. Energy does not change because box length is same. Okay. The normalization constant for the first excited vibrational state of one-dimensional simple harmonic oscillator is. Okay. Normalization constant they are asking. You know very well. I already discussed this. Normalization constant depends on the vibrational state. What is the formula? Normalization constant for nth vibrational state is given as alpha by pi whole power 1 by 4, okay, divided by square root of 2 power n into n factorial. Remember this formula. This is the formula for normalization constant. Alpha by pi 1 by 4, it is a constant, keep it as such. It depends only on the oscillator. So keep this alpha by pi 1 by 4 as such. Now, the question is for the first excited vibration state. You know when ground state is n equal to 0. First excited state is n is equal to 1. Sorry. N is equal to 1 means it is first excited state. Excited state. So put n is equal to 1 everywhere. So 2 power 1, 1 factorial. 1 factorial is 1, 2 power 1 is 2. So we get the answer is 1 by square root of 2 into alpha by pi whole power 1 by 4. So the correct option for this question is option B. Okay, take it. Question number 6. Hermite polynomial for n is equal to 3 vibrational state of a one-dimensional simple harmonic oscillator is where q is equal to root alpha into x. Okay, 4 options are given. Yes, you try to answer it. I have told you, listen, for Hermite polynomial, listen, Hn of q, right? It takes different terms. The number of terms depends upon the value of n, whether it is odd or even. Suppose if n is even number, then you will get the first term. First term is 2q power n. Always first term is 2q power n. And second term is, you will get some constant, say b into q power n minus 2, right? Then plus c. Okay, so you will get up to a constant term. Okay, you get many terms, and final term is a constant term. Whereas if n is odd, the first term is 2q power n as usual. Second term is b into q power n minus 2, where n is odd now, okay. And the final term is actually some c into, or some constant into q. Final term is not a constant. It will end up with the q if n is odd. Is this clear to all? So, in the given problem, n is given as 3. If n is 3, then the Hermite polynomial for h3 of q is, yes, what will get? The first term is 2q power 3, correct? 2q power 3. And second term, q power 3 minus 2 will get q. So, you will get some value into q. Right. So, what is the term? 2 power q is, 2 power 3 is 8. 8q cube plus some q term should be there. There should not be any constant. There should not be any square term. Are you able to follow? Now, you just compare the options. If you compare the options, yes, you can easily find out. See, I have 8q cube. Q square is there. Q square is not possible because if q is power n is there first term, second term should be q power n minus 2. Okay, so q square is not possible. And in option B, yes, q power 3 is there. If you subtract 2, I'll get q. Yes, it ends with the q. The term ends with the q. Yes, this is correct. Whereas in option C, q cube is there and q term is there, and final constant is not possible for odd numbers. If n is odd number, constant is not possible. If n is even number, you will get constant. If n is even number, you will get constant. If n is odd, constant is not possible. So here also some constant is given, it's not possible. So the only correct option is option B. Okay, so for this case, the correct option is option B. Okay, is this clear? Listen. Question. Yeah, so next question is this, question number 7. For a one-dimensional simple harmonic oscillator, dou psi naught, that is ground state wave function, okay, differential of ground state wave function with respect to x at x equal to 0 is. Yes, what will get? Listen, for the ground state, psi naught means ground state. Psi naught represents ground state wave function. Ground state wave function. Okay, listen, the ground state wave function, this is wave function, ground state wave function, and this is the x-axis. Here I have plus x, here I have minus x, and the function goes like this. Ground state wave function goes like this. It will approach 0 when x approach plus infinity and minus infinity. Now listen, this is x equal to 0. At x equal to 0, what is the first derivative? You know very well, first derivative is nothing but tangent at x equal to 0, correct? Yes, d psi naught by dx is nothing but slope. Slope of the straight line which is drawn at x equal to 0. So at x equal to 0, you draw a straight line. Okay, what is the slope of the straight line? Slope of this straight line, slope is nothing but d psi naught by dx at x equal to 0. Listen, since this line is parallel to x-axis, slope of this line is 0. Slope of this line is 0. Right? Take it. You know very well, this is another route possible. the ground state wave function for one dimensional simple harmonic oscillator is alpha by pi whole power 1 by 4 into e power minus alpha x square by 2. This is the ground state wave function formula. Now differentiate this with respect to x and put x equal to 0. So if I differentiate this d psi naught by dx, first I will differentiate. So this is constant, keep it as such, alpha by pi whole power 1 by 4. If I differentiate e power term, I will get the same thing, e power minus alpha x square by 2. Then in the numerator we have minus, you keep alpha by 2 as such. If you differentiate x square, I will get 2x. 2 cancel. So we get some quantity minus alpha by pi into whole power 1 by 4 into x. I have one x here, into x, and I have an alpha, so I will put alpha in front, alpha into e power minus alpha x square by 2. Okay, but we need to find out this d psi naught by dx at the x equal to 0. If you put x 0, the entire quantity becomes 0. Okay, so we can find the first derivative using this technique also. Okay, right. Question number 8. The product of delta x into delta px, product of two uncertainties for the ground state of one-dimensional simple harmonic oscillator equal to. You know very well, the product of the uncertainties delta x into delta px. The product of these two uncertainties is equal to n plus half into h cross by 2. Am I right? Is the formula correct? Check it.
Sir.
The product of these two uncertainties depends on the quantum state, the vibrational quantum number. Okay. For ground state, n is equal to 0. If I put n equal to 0, I will get 0 plus half, right, into h cross by 2. Right? I'm sorry, I made a mistake, right? This is just h cross, right?
H cross.
Yes. This is n plus half into h cross only. I'm sorry. Right? So we get the answer as h cross by 2. Take it. The correct option for this question is option B. Okay? So it's simple. Yes, what's the question asked? The number of nodes in the state psi 5 of x of one-dimensional simple harmonic oscillators. Number of nodes. Listen. Yes, this is a direct question actually. Question number 9. Listen. For one-dimensional simple harmonic oscillator, okay, we give the wave function as psi n of x. And n starts from 0. n 0, 1, 2, 3, 4, etc. If n is equal to 0, there is no node. If n is equal to 1, we have one node. If n is equal to 2, we will have two nodes. Therefore, number of nodes is equal to n. Number of nodes is equal to n in this case. Okay, for n is equal to 5, see, psi 5 of x means n is equal to 5. For n is equal to 5, there should be 5 nodes. So the correct option for this question is option B. Okay. Question number 10. For a one-dimensional simple harmonic oscillator, the expectation value of kinetic energy for n is equal to 5 states. For one-dimensional simple harmonic oscillator, what is the expectation value of kinetic energy? We know very well. Expectation value of
4.
Yes. Expectation value of kinetic energy equal to S by S plus 2, okay, into energy of the nth state. Is this correct? Check it.
Correct.
Now listen, what is S here? For one-dimensional simple harmonic oscillator, potential energy is equal to kx square by 2. So the variable x has power 2, so S value equal to 2. Put S is equal to 2 here, so we get 2. If we put 2 here, 2 plus 2, 4 into
4.
Energy of the n equal to 2 state, right? Energy of the n equal to, energy of the n equal to 5 state. For En5, what is the formula? 5 plus half into h nu. Energy formula for nth vibration state is n plus half h nu. Since n is 5 here, so put 5 plus half into h nu. So what we get is, this is 2 by 4. If you cancel it, you will get 1 by 2 into 5 2s are 10, 10 plus 1 11. So 11 by 2 h nu or 11 by 4 h nu is the answer. So the correct option for this question is option D. Okay, take it. We have already completed translational motion and vibrational motion. Now we will discuss about rotational motion. Rotational motion. Yes, what is this? Rotational motion. Observe carefully. In rotational motion, we have 4 systems. Number 1, we have 4 systems. Number 1, particle on a ring system, particle on a ring. Okay, here mass of the particle should be given as m. Number 2, particle on a ring, particle on a sphere. Here mass of the particle is given as m. Then number 3, rigid rotor. Okay, I'll take specifically diatomic rigid rotor. Diatomic rigid rotor means diatomic molecule behaves as rigid rotor. Diatomic rigid rotor, okay, in 2 dimension. If rotation occur in 2 dimension, then you should put mass as reduced mass. Okay, number 4, rigid diatomic rigid rotor in 3 dimension. Yes, here also you must put mass as reduced mass. Okay, listen, this and this, first and third, they are one and the same. You will get same formula, same wave function formula, everything. What is the only difference? In the case of particle on a ring, you should put mass as m. In the case of rigid rotor in 2 dimension, you should put mass as mu, reduced mass. Similarly, second system and third system, fourth one, they are one and the same. Okay, they are same. Here also they are same. What is the only difference? See, you will get same energy formula, you will get same wave function formula, everything same. What is the only difference? Here you put mass as m, here you put mass as reduced mass. Okay, is this clear to all? So listen carefully. First system and third system, they are one and the same. Only difference is, here we should put mass as m, here we should put mass as mu. That's all. Okay, so listen carefully. We'll start with the first system, first and 3. That is particle on a ring. Particle on a ring. Okay. Whatever that I am going to discuss here, it is applicable for rigid rotor in 2 dimension also. Okay, particle on a ring. So I have a ring with a constant radius. Listen, with a constant radius, and let us assume your particle is moving, right, along this ring. So when the particle moves along the ring, radius remains constant. Radius remains constant. Okay, right? Yes. Listen, in this case, let us take this axis as, say, x-axis and this axis as y. Okay, it's up to you. You can take this as x, that's as y. Okay, it's up to you. Now, see, this particle is moving in the xy plane. Particle is moving in xy plane along the ring of constant radius. Along the ring of constant radius. Radius remains same. Okay. Therefore, when the particle moving along this xy plane, observe carefully, x value will change, y value will change, but z remains constant. So here z is, let me take that z as 0. Z variable value is 0. Therefore, wave function of this particle depends only on the 2 coordinates x and y. Okay, but since the particle is moving on a ring, remember, whenever particle is moving on a ring or a sphere, then it is better to use spherical polar coordinate rather than Cartesian coordinate. Okay, so what is the corresponding spherical polar coordinate? Right, if you use spherical polar coordinate, you will get r, theta and phi, but here r is constant, right? The particle is moving with a constant radius, so r is constant, remove r. Okay, remove r. Then what about theta? Theta is the angle between z-axis and xy plane. I am sorry, in this case, the particle is moving in xy plane, the angle between z-axis plus z-axis and the line joining the origin and the particle. Okay, it is exactly 90 degree, which is also constant, so remove that. Therefore, observe carefully, the wave function in Cartesian coordinate depends on two variables, whereas the same wave function in spherical polar coordinate depends only on one variable. Okay, so it is easy to discuss the changes or whatever property that we are going to measure, right? All those things are very easy if I give wave function in terms of spherical polar coordinate, because wave function depends only on one coordinate now. So that is the reason why for particle on a ring we use the spherical polar coordinate. Okay, wave function which depends on phi, it is usually represented as big phi. See, wave function which depends only on phi is usually represented as big phi. Okay. Now, what we have to do? We need to solve the Schrodinger equation. So, what is the Schrodinger equation? H psi. Now, instead of psi, I put this H phi, which depends on the variable phi, is equal to energy into the same wave function. Okay. Now, what is the Hamiltonian formula? Listen, since the particle is moving in xy plane, okay, listen, observe carefully this is very important. Hamiltonian means total energy. Since the particle is moving on a constant radius, potential energy is constant in this case, because radius is constant. Potential energy constant, so we can assume it as 0 for our convenience. Since potential energy is 0, so Hamiltonian operator contains only kinetic energy part. Okay, we know very well what is kinetic energy. In classical formula, K is equal to half into mv square, or we can write T is equal to P square by 2m, alternative formula. Okay, P square by 2m, right? Now observe carefully. T is equal to, I'll keep this 1 by 2m as such. What is P square operator? So, very kinetic energy operator. Okay, 1 second. Listen. So, we know very well kinetic energy. Let me change this. Kinetic energy equal to half mv square. Okay. Now, I am going to write the kinetic energy in terms of angular momentum. Yes, how to do? Very simple. Very simple. You know very well, the linear velocity v is equal to r omega, where omega is the angular velocity or angular frequency. Substitute this here. So, T is equal to half into m into v square r square omega square. R square omega square. Now, what I am going to do? I am going to multiply the numerator and denominator by m. So, what we get is T is equal to, okay, I'll get m into r into omega the whole square, okay, by 2m, sorry, 2m. Okay, take note. So, we know very well, yes, listen, so I said kinetic energy equal to half into mv square, okay. This is the formula for kinetic energy. Now, what I am going to do, I will multiply numerator and denominator by m into r square. Okay. So, I will multiply numerator by m into r square. So already we have mv square. Now I am multiplying the numerator by m into r square, and I am going to multiply denominator also by m into r square. So if you multiply same quantity in the numerator denominator, nothing going to change. M into m is m square, r square, so I can combine this mvr whole square by 2 into, what is m into r square? M into r square is nothing but moment of inertia. So kinetic energy equal to, what is mvr? M into v into r, angular momentum. So yes, L square by 2I. This is the general formula for kinetic energy in terms of angular momentum. Now observe carefully. Since the particle is moving in xy plane, the angular momentum exists only along plus z axis or minus z axis. Only z component of angular momentum exists because the particle is moving in xy plane. There is no Lx, Ly. So listen, you know very well, L square operator can be written as Lx square operator plus Ly square operator plus Lz square operator. But since the particle is moving only in xy plane, these two are 0. Okay, x component, y component is the only component that remains is z. Therefore, instead of L square I can write, therefore kinetic energy operator equal to Lz square operator by 2I. Lz square operator by 2I. This is the kinetic energy formula. And since potential energy is 0, right, Hamiltonian is also equal to the same thing. Okay, 2I into Lz square operator. This is the Hamiltonian operator formula. Take note. I am applying Hamiltonian operator on the wave function. If you get same wave function multiplied by E, then E is called energy eigenvalue and phi is called eigenfunction. Now listen, what is Hamiltonian operator? Just now we discussed, it is nothing but 1 by 2I into Lz square operator into phi, right? E into phi. Okay, we also know that what is Lz operator. See, Lz operator, we know very well, is equal to minus I h cross into dou by dou phi. This we know. Then what is Lz square? Take the square of this. Minus, if you square it, it will become plus. I square is minus, so you put minus again. H cross square, and this become dou square by dou phi square. So let me write d square by dp square, because I have only one variable now. So this is the Lz square operator. I'll substitute this. So if I substitute this, I'll get minus h cross square by 2I into d square big phi by d small phi square equal to E into big phi. Yes, this is the equation we need to solve. I am not going to do that. Okay, you know very well, it is a simple one. It is available in all books. So what I am going to do, I am going to give you the final answer. Okay, for derivation part, I will send the video lectures, right, which I recorded already. I will send to you. You just go through. Now listen, if you solve this, you will get the wave function. You will get the normalized wave function. So what is the normalized wave function? 1 by square root of 2 pi into e power I m phi. This is the wave function formula. Okay, 2 pi, this 1 by square root of 2 pi is the normalization constant. E power, I have complex quantity. M is the quantum number which can take value 0, plus or minus 1, plus or minus 2, etc. Phi is the variable. This is the wave function for particle moving on a ring. Observe carefully, this is not mass. M is not mass here. Okay, keep that in mind. M is a quantum number here. So, to differentiate this quantum number, I will put ML. I will put ML just for identification purpose. Okay, ML means it's a quantum number, it is not mass. Okay, now what is the energy formula? Energy depends on the quantum number ML, which is given as I'll put it here, h square by 8 pi square I into ml square. This is the formula. Taken? This is the energy formula. Energy depends on the quantum number m. Okay? Taken. For particle on a ring, what are the allowed values of energies? Listen, when ml equal to 0, that is the lowest possible quantum number. If I put ml equal to 0, what is the energy formula? E energy depends on the quantum number ml, which is given as ml square into h square by 8 pi square I. This is the formula. Okay, and here this h square by 8 pi square I is sometimes called as rotational constant in energy unit, joule unit. Okay, this is rotational constant, right, in joule unit, rotational constant in joule unit. Okay, so instead of h square by 8 pi square, I can write simply V. Now, so energy formula is ml square into V. What are the allowed values of ml? 0 plus or minus 1 plus or minus 2, like that it goes. First I'll put ml equal to 0. If I put ml 0, then the entire quantity becomes 0. So the lowest possible value of energy, right, if you put ml 0, okay, you get that E0, that is 0. Lowest value of energy for rotation is 0. So for rotational motion, okay, 0 point energy is 0. There is no 0 point energy. Then what is the next higher energy? Put ml equal to plus 1 or minus 1. If I put plus 1, if you take square, it becomes 1. 1 into B is B. If I put minus 1, if you square it, you will get again plus 1. Plus 1 into B is B. So for ml plus 1 and ml minus 1, I will get the energy as B. Therefore, listen, for energy, for ml plus 1 or minus 1, we get the energy as B. So these two states, that is ml plus 1 state and ml minus 1 state, they have same energy. They are called doubly degenerate states. Doubly degenerate state. Now, we'll move on to the next level. Put ml equal to plus 2 and minus 2. If we put plus 2, 2 square is 4, 4 into B is the 4B. If you put minus 2 square, if you take square, I'll get again 4. 4 into B is 4B. Therefore, ml plus 2 and ml minus 2 also give me the same value of energy, which is ml plus or minus 2 equal to 4 times B. So what does this indicate is that except the ground state, all the other energy levels are doubly degenerate. Doubly degenerate. Except the ground state, all the energy levels, okay, except the ground level, all the other energy levels are doubly degenerate. Okay, keep this in mind, very, very important. Listen, since the particle is restricted to move on a ring of constant radius, it is restricted to move on a ring of constant radius r, okay, constant radius r, and it rotates in xy plane. We assume like this. We assume that the particle is moving in xy plane. We assume like this. Therefore, x component of angular momentum is 0. Y component of angular momentum is 0. The only angular momentum exists is z component of angular momentum. This is the only angular momentum exists. Okay, what is the magnitude of the angular momentum? Okay, magnitude means just Lz. What is the value of Lz? Magnitude. How to find? It's very, very simple. Listen. Yes, we need to solve the Schrodinger equation actually. We need to solve the operator. So you take the Lz operator. apply this operator on the function phi. Okay, so what is LZ operator? Minus I h cross, I have given already, minus I h cross d by d phi. This is LZ operator. Now what is phi? Phi is 1 by square root of 2 pi into e power I into m into phi, ml into phi. Okay, this is the wave function formula. Now you have to differentiate once. So what to do? Keep this minus I h cross as such. 1 by square root of 2 pi is a constant, keep it as such. Now differentiate this. E power, if you differentiate, you will get the same quantity. Exponential and differentiation will give the same thing into power. In power we have I into ml into phi. I am differentiating with respect to phi, right? So phi become 1. So 1 into IML. So I will get I into ml. Okay, so listen. I into I is I square. I square is minus 1. I have minus already. So minus or minus become plus 1. And I have h cross. H cross into ml. H cross into ml. And square 1 by square root of 2 pi e power I n phi is my wave function. See, I have applied this operator on the function. I got the same wave function as result. Therefore, phi is an eigenfunction of LZ operator. And this is the eigenvalue or magnitude. So what is the magnitude of angular momentum? Z component of angular momentum is nothing but ml into h cross. Take this. Magnitude of angular momentum, Z component of angular momentum is ml into h cross. I told you already, x component, y component are 0. Only z component exists and the magnitude of z component of angular momentum is ml into h cross. What are the allowed values of angular momentum, z component? Put ml equal to 0 first. So if ml 0, then the lowest angular momentum is 0. Then put ml plus 1 and ml minus 1. So you will get plus h cross and minus h cross, plus or minus. Then plus or minus 2 times h cross. Like that, you will be having quantized angular momentum is a component of angular momentum. Right? So whatever that I have discussed here, this is the energy formula for particle on a ring, and same energy formula is applicable for a rigid rotor in 2 dimensions. I have already told you, particle on a ring, rigid rotor in 2 dimensions, they are one and the same. Okay, right. So I stop here. In the next class, we will discuss about the particle on a sphere or rigid rotor in 3 dimensions. Okay.